Here we have another example of a linear system, and it is again another physical type of situation that will be able to transform into a linear system and solve a problem, right? We're problem solvers, and linear systems are our tools of the moment. So this particular topic comes from an area of physics called thermodynamics, and just in again, without getting into any great detail, but thermodynamics is the study of things like heat, temperature, energy, etc., and the relationship amongst them, right? So, how are these quantities related? And there are other things too. It's not just this, but this is a just a very light definition. So, and the relationship or ships amongst them, right? If you are a mechanical engineer, you look at course of study as an undergrad, you'll see courses in thermodynamics listed there. Maybe sometimes 2 semesters of thermodynamics. So you can fill an entire year's worth of study with this material. Obviously, that's not what we're doing now. We just want to state a fairly simple problem and then show how it's related to a linear system. All right, so here is the problem. And this particular problem is a two-dimensional problem. So let's say you have a thin plate like this, right? So this is a thin plate. And the fancy word for something like that is a lamina, right? And you might recognize that it's related to the word laminate, right? So you get that thin plastic cover on whatever object it is you're trying to protect. So we have one of those thin things here, and what happens is along the borders or boundaries, it's controlled at a constant temperature. So the boundary is held at a constant temperature. Right? Now, it doesn't mean it has to be the same all the way around. It could even be, so what I'm going to do is I'm just going to highlight a few points along the boundary, right? And so at these points, the temperature will be known, so whatever your scale is, not worry about the scale right now, but let's say your temperature of 10 maybe degrees Celsius is on this side. Here maybe it's 20. You could even have different temps at different points along the same boundary right here. So you could have 15 there, 20 there, and then let's say you have 25 there, and maybe even 30 there, right? So you have these points along the boundary at which the temperature is held constant, right? And then the question is, what is the temperature at the interior of these this thin plate, right? Now, if I were to think of this plate as a continuum, so like one nice continuous object, the exact solution to this problem, right, where we would try to find the temperature at the interior points here would require some pretty advanced calculus, right? So that's not what we're going to do. We're going to say, okay, I want to know the temperature at just specific points. So what I'm going to do is form this grid. So we got a few more horizontal lines there, a couple vertical lines there. And then where these intersect, I'm going to have some other points, and these are the points at which I want to know the temperature. So let's label them. So at this point, there's a temperature of T1. At this point, there's a temperature of T2. At this point, there's a temperature of T3. At this point, there's a temperature of T4, right? So again, so now here, so what I'll do is over here, here's my question, right? What is T1 through T4? So what is T1 through T4? As I stated earlier, if we were to do this to get the exact, like to figure out the temperature function, right? And they're under certain hypotheses, and again, using some pretty fancy calculus, we could get a temperature function that would give us the temperature at any point at the grid, right? In this grid. But that's not what we want, right? We're willing to live with an approximation. So here is the principle that will lead us not to calculus, but instead to linear systems. So here's our principle. There's always a guiding principle that you use to kind of come up. Okay, this is what we're going to use, and this is the type of solution it allows us to use. So the principle is this: at each interior node or point, right, its temperature is approximately, so its temperature is approximately equal to, so it's approximately the average of the 4 surrounding temperatures. Right? So if we have one of these interior nodes and we are willing to settle for an approximation of the temperature, right, we can use this principle where it says it's the average of the 4 surrounding temperatures, right? So again, what that is saying is, for instance, if I want to approximate T1, what would I do? Well, I would take the average of 10, 20, T2, and T3, right? So these are the 4 surrounding temperatures of T1 are 10, 20, T2, and T3. Right? So let's start writing down some equations, because we know how to find the average of something, right? So for T1, so T1 is equal to, it would be, or it is 10 plus 20 plus T2 plus T3 all over 4, right? Again, that's how we take an average. You sum up the 4 quantities, you divide by 4. And we can do this for the remaining 3 temperatures. So T2 is equal to, now its 4 surrounding temperatures are T1 and T4, which are unknown, and then 20 and 15 that are held constant. So T2 is equal to the sum of T1 and T4 and 20 and 15. And then again divided by 4 for that average. For T3, the 4 surrounding points are T1, T4, and then we have a 10 and a 25. So T3 is approximately equal to T1 plus T4 plus 10 plus 25 divided by 4, right? Now, I know I am writing the equal sign, but that's why I keep saying approximately equal, right? Um, and then finally T4. So let's see, what's the expression for T4? So we're going to sum up T2, T3, 20, and 30. So T2 plus T3 plus 20 plus 30 all over 4. And that gives us the average, which is going to be approximately equal to T4. So these are the 4 linear equations that we need, right? 4 equations, 4 unknowns. Let's continue working through it. And again, like the previous applications, we'll take it to where we express it in an augmented system. Because once you get it to that point, then the processes of Gaussian elimination or Gauss-Jordan elimination will kick in, right? But the skill that's being described or illustrated here is how we can take this, right? And with this principle, turn it into a linear system. All right, so we have our equations and everything is over 4. Well, initially, if you want to avoid fractions, and it's highly unlikely that you would go through the complete solution of this particular problem and never have to deal with fractions, right? But let's say you want to clear fractions from the outset. One of the easiest ways to do it is to multiply each of these equations by 4. So we would have 4t1 is equal to, and then here, t2 plus t3 plus 30, right? So that would be our equation 1. Our second equation would be 4t2, and then that will be t1 plus t4 and plus 35. Equation 3 is 4t3, and then that's equal to t1 plus t4, and then we'll have 10 plus 25, so that's 35, like that. And then finally 4t4, and then we will have t2 plus t3, and then this will be plus, not 15, but 50, all right? So getting closer to the way we typically write our systems, but now let's get all the variables on one side. So, you know, our variables on the left and our constants on the right. And then I'll just kind of write it in the middle now. So taking this first equation and subtract t2 and t3, we will have this. 4t1 minus t2 minus t3, there's no t4, that has to be equal to 30. Taking the second equation now, subtract t1, so you'll have a minus t1, and then you'll have a plus 4t2, so now we're arranging our variables in that standard form, and then minus t4, right? That's equal to 35. And then now our third equation, subtract t1 again, so you'll have a negative t1. There's no t2 now, and then we have a plus 4t3, and then a minus t4, and that's also equal to 35. And then finally now, the fourth equation, there is no t1, but there's going to be a negative t2, and a negative t3, but then a positive 4t4, and then that's equal to 50. And let's do our last step in creating this augmented system. And when you look at the system for these temperature approximation problems using this particular principle, there's such a nice pattern to it. The first row is 4, -1, -1, 0, and then we have our constant over there, 30. Then we have -1, 4, 0, -1 right there. And then what do we have there? 35. Yep. And then the third equation is -1. Then we have 0, and then 4, and then -1. And then that's also 35 on the right. And then finally, -1. Oh, sorry, 0, not -1. That would break our nice pattern, which I'm sure you can see by now. You have 0, -1, -1, 4, and then 50, right? So I'm going to scroll back up now to see where we started. We started with this thin plate, this lamina, and we have a temperature controlled border, very precisely controlled. And we want to approximate the temperature at these 4 interior nodes of this plate. And we used this principle, and it seems like a fair principle when you think about it, right? You know, the average, let's say, in the middle is, the value in the middle is just going to be an average of the surrounding temperatures. It doesn't seem so far-fetched, and it's a very, very useful principle. But based on that, that grid turns into this augmented matrix. Again, if you know, if you don't have goosebumps right now, I don't know, check your pulse. It shows again the power of math, and I will preach that until I can't preach anymore. Okay? So I hope you found this one interesting. It's certainly different from all the applications that we've looked at up to this point, but it's no less important, right? So now I know you're dying to see what I have left. So see you in the next video.